Greetings to Dr. RAMHUZAINI. We are from Group 5 of Section 6. We'll present about our project. That is, we conduct the project of water level control system. This is my team in this project. That is me, myself, as NICOLLE KALONG, CD230038 as the project manager, MOHAMMAD AKMAL bin ARZMI, which is he is the project engineering manager, Muhammad Nabil bin Muhammad Shukor as the quality control manager, and Muhammad IHSAN bin SHAMSUDIN as the simulation and data analysis engineer. So in this video presentation, we will talk about the introduction of our project, the literature review, mathematical modeling, the analysis we found, the results and the discussion, and of course the conclusion and the recommendations.
Assalamualaikum and hi, my name is Muhammad Akmal bin ARZMI, metric number CD220005. Introduction to water level control. Water level control is critical in industries such as food processing, power generation, chemical manufacturing, and wastewater management. It ensures safety, efficiency, and reliability in these operations. The system works by using sensor to monitor the water level, a controller to compare the level to a set point, and an actuator such as a water pump or valve to regulate the flow. This closed-loop feedback mechanism keeps the water level stable, even during process change. The main objective of the water level control is to maintain a consistent level for safe, efficient, and continuous operation. It also helps prevent overflow, underfill, and system failure. This is important because it avoids safety hazard, process interruption, and equipment damage. At the same time, it enables automation, provide faster response, and reduce costs. In the past, water level were controlled manually, which often led to error and delay. Today, automation allows real-time adjustment, offering higher reliability and improved system performance. Our literature review. Process control is essential for safe, efficient, and reliable operation in industry like water treatment, chemical processing, food production, and power generation. It manages key variables such as temperature, pressure flow, and water level, reducing error and waste while meeting quality standard. A control quality has four main components, such as sensor to measure water level, a controller to compare it with the set point, actuator like pump or valve to adjust flow, and a feedback loop for real-time stability. Control methods have evolved from manual operation to pneumatic and digital system, then to distribute control system. Today, with Industry 4.0, modern system use SCADA, PLC, IoT, and AI for smart automation. Challenges still exist, such as maintaining accuracy, high implementation costs, cybersecurity risks, and sensor failure. Water level is chosen as the control variable because it's common in industry, simple to model, and easy to simulate. Its main goal is to prevent overflow and underfill for safe and continuous operation. The system uses a closed-loop PID controller, which minimizes error and stabilizes the water level near the desired set point.
Greetings to Dr. Ram. I am NICOLLE KALONG, CD230038, and I will be present about the mathematical modeling. My part is the mathematical modeling of this water tank system that our group is conducting this project, and we found out the transfer function of it. The mathematical model of the water level control system is based on the principle of mass balance. This is which states that the rate of change of water volume in the tank are equal to the difference between inflow and outflow. So I did the derivation of the control system based on the equation below. The equation below states that the Q in over T minus by Q out over T. By deriving the equation in here, we will after that substituting into the equation and applying the Laplace transform yields the transfer function of the tank. This is our transfer function for the tank, which is H over S is input and the Q in over S is the output. And it turns out to be 1 over AS plus 1 over R. This first order transfer function represents the dynamic response of the water level to change in the inflow. It is then combined with the actuator gain to form the open loop model, and finally integrated with a PID controller to form a complete closed loop system used in the performance simulation and control analysis. For our open loop transfer function, we assumed a valve gain kV where Q in over S is equal to kV times US. Our transfer function for open loop is kV times Utex, which is it will turns out to be kV over AS plus IR. The derivation of the tank transfer function is based on fundamental principle of mass balance, system linearization, and Laplace transformation. By linking the dynamic behavior of the tank with the control input through this mathematical model, we establish a solid foundation for understanding both the open loop and closed loop system behavior. This approach ensures our control system design is grounded in physical reality and can be confidently analyzed using simulation tools such as MATLAB Simulink.
So for the system analysis, we obtain two bot plot from the open loop transfer function and the closed loop transfer function. For the open loop bot plot, it shows a smooth negative 20 decibel per decade slope typical of a first order system. The phase gradually drops to negative 90 degree, confirming the low order system behavior. No gain crossover, showing that infinite phase and gain margin shows that the system is very stable but slow. For the closed loop dot plot, the magnitude rolls off more steeply at higher frequencies, with improved disturbance rejection and better high frequency attenuation. The sharper phase transition shows a stronger dynamic response from feedback. In conclusion, the closed loop system has better frequency response and enhanced stability due to PID. Moving on to the Nyquist plot. So we obtain two Nyquist plot from the open loop transfer function and the closed loop transfer function. On the open loop Nyquist plot, we obtain a smooth elliptical curve, symmetric and far from the critical point, which is the negative 1, 0. So it confirms that the system stability and low sensitivity in gain changes, and the trajectory never circles or touches the critical point. For the closed loop Nyquist plot, it shows a smaller and tighter curve near the origin, which indicates a higher damping in the system. It shows that the improved robustness with stronger feedback influence. In conclusion, both systems are stable, but the closed loop transfer function is more robust to changes in gain margin.
Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Muhammad Nabil bin Muhammad Shukor. My metric number CD220046. I will continue with the next presentation. Okay, let's start with the root locus analysis, which is a graphical method used in control system to study how the poles of a system change with variation in controller gain. In this case, the PID gain. As shown in the plot at the center of the slide, we can observe the root locus of the open loop system with a PID controller applied. Each pass represents how the closed loop poles shift as the controller gain increase. Okay, firstly, we notice that as PID gain increase, the pole tend to move further into the left half of the S-plane. This movement is important because pole of the left half indicate a stable system. However, we also observe that some of the branch curve back toward the right half of the plane. This is a critical insight. It shows that if the gain is pushed too far, the system could become unstable. This path entering and approach the right half plane indicate the limit of PID tuning. Okay, using this root locus plot, we were able to select optimal PID value that keep the poles in a region that offer good damping, meaning we avoid excessive overshoot while still achieving a responsive system. Moving on to the step response analysis, which help us to evaluate how the system responds over time when subject to a sudden change or input. Okay, let's begin with the open loop response shown in the top graph. The tank level rise very slowly, indicating poor responsive. Even after a long duration, the system only reached about 0.48 instead of the target value of 1.0. This shows the presence of a large steady-state error, which is undesirable in most control systems. On the positive side, we can see there is no overshoot, meaning the system is stable. But clearly, the tracking performance is weak and not suitable for and fast or accurate application. Okay, now let's examine the closed loop response with PID control shown in the bottom graph. The difference is immediately noticeable. The system now reached the desired level of 1.0, completely eliminating the steady-state error. The rise time is much faster, and although there is a slight overshoot of around 25%, this is acceptable and can be further tuned if necessary. Additionally, the system settled to its final value much faster, with a settling time of about 400 seconds, which is a significant improvement from the open loop case. Okay, conclusion from what we get, the PID controller has significantly enhanced the system performance by providing faster response, eliminating steady-state error, and improved accuracy and stability. This demonstrates the effectiveness of applying feedback control in real-world system. The last part is conclusion. To conclude, this project has successfully developed and analyzed a PID-based water level control system using both mathematical modeling and simulation techniques. We begin by modeling the system using Maxwellian equation and applying the Laplace transformation, which led us to a first-order transfer function that accurately represent the tank dynamics. When observing the open loop response, we found that while the system was inherently stable, it exhibit a slow rise time and a noticeable steady-state error, indicating poor performance in terms of speed and accuracy. To overcome this limitation, we designed and implemented a PID controller. The result was significantly improved. The closed loop system displayed a faster rise time, a reduction in overshoot, and a complete elimination of steady-state error. After careful tuning, we selected the PID parameters as Kp equals to 4.4, Ki equals to 1.8, and Kd equals to 4, which produced a response that was stable, accurate, and well damped. Overall, this project clearly demonstrates the value and effectiveness of control engineering in addressing the real problems. The use of PID control not only enhances the system performance but also provides valuable insight into the design of automated process control system commonly found in industry. That's all from us. Thank you.